Welcome to our Back to through Inquisitive Kids. In this video, we will be looking at the lesson Itinerary Problems using Systems of Equations. Applying your knowledge of systems of equations to solve basic itinerary problems. First, what are itinerary problems? Itinerary problems are any type of problem that involves speed, distance, and rate. This could be talked about if a train was trying to get from point A to point B, a kid was trying to get from the bottom of the stairs to the top of the stairs, or a boat in the water trying to go from harbor A to harbor B downstream and then upstream back again, B to A. If you're interested in itinerary problems specifically, I have some more challenging problems these that are given in math competitions that if you're just interested in, you could just go and look and watch. So I will be putting those links in the description down below if you're interested. Okay, so this is part 3 of Systems of Equations in Real Life. The 2 learning goals for today is to solve itinerary problems using systems of linear equations in 2 variables, and of course to continue experiencing what it's like to solve word problems with systems of equations. This is a skill that is so basic. It's important, but I would call it basic because so many other skills are sprouted off of your basic knowledge of systems of equations. So it's so important that you really strongly and firmly grasp the steps of solving word problems using systems of equations. Let's look at introduction. Answer the following questions using a whole expression. The tens digit of a 2-digit number is x and the ones digit is y. So therefore, the value of the 2-digit number can be expressed with a whole expression. So if the 10th digit is x, its real value would be 10 times x. And if the ones digit is y, its real value would be 1 times y. So the final answer would be 10x plus y. The hundredths digit of a 3-digit number is A, and its tens digit is B, and the units digit or the ones digit is C. Therefore, this 3-digit number can be expressed as, using what we did from the last problem, this is just with a 3-digit number, so you have 100A plus 10B plus C. Solving word problems using systems of equations. Here's our warm-up. Use variables to represent unknowns. A 2-digit number with a units digit of A and a tens digit of V can be expressed as blank. If you swap the order of these 2 digits, you can express this new number as blank. So it's just 10B plus A and 10A plus B. Use variables to represent unknown multi-digit numbers. So now it's not just representing unknowns, because in the past, A and B were the digits. Now, how can we use them to express multi-digit numbers? With 2-digit number x to the left and 2-digit number y to the right, so now x and y representing 2-digit numbers. A new 4-digit number is formed. Use x and y to represent the value of this 4th-digit number. Conversely, if you swap the order of x and y, the new 4-digit number that is formed can be expressed as blank. So we know that x really takes up 2 place values, right? So if this is forming into a new 4-digit number, this part is x. Oh, that's ugly. So it would look like this part would be x, and this part would be y. Right, and if we're going to use the values of x and y to represent this 4-digit number, you shouldn't say 10x plus y anymore, because y already takes up both the units digit and the tens digit. So you would have 100x plus y. So this is something that's very important. It's not 10x plus y, it's instead 100x plus y, because be mindful of how y is actually a 2-digit number. It takes up 2 place values. So conversely, swap the order, you have 10y plus x. A 2-digit number with m in the ones place and n in the tens place. If you add a 0 in between these 2 digits, the new 3-digit number would be, well, it's first m and n, right, in their place values. Now it becomes a new 3-digit number. So you have m followed by a 0 followed by a n. So really you could just do 100 times m plus n. Alright, so this in the wrong order, should be 100m plus n. Alright, so now let's look at this word problem. Karen and her family is driving by car at a constant speed. So when it says constant speed, right, so the speed doesn't change. The following are the 3 different sights Karen saw on the trip, each separated by 1 hour's time. So as you can see, this is 2 p.m. 12 p.m. This is 13 p.m. or also 1 p.m. This is 2 p.m. or 14 p.m. Can you determine the number on the sign that Karen saw at 12 p.m.? So see how each of these says have a sign? Well, these signs have numbers that show you how many more miles or how many miles you've already went. And since she's driving by constant speed and they're separated each by the same amount of time, 1 hour, you can infer that the distance from 12 p.m. to 1 p.m. is the same as 1 p.m. to 2 p.m. So now we have 3 clues. The 2-digit number, so this one here is a 2-digit number with the digit sum as 7. So it's a 2-digit number that has a digit sum of 7. Here at 1 p.m., the 10th digit and the 1st digit have exactly swapped since 12 p.m. and 2 p.m. There is an extra 0 between the 2 digits of the number seen at 12 p.m. So following these 3 clues, can you find the number on the sign that Karen saw at 12 p.m.? Well, we start by taking the unknowns and setting them as variables. If the 10th digit of the sign that Karen saw at 12 p.m. is x and the 1st digit is y, then the number she saw at 12 p.m. can be expressed as 10x plus y. The number she saw at 1 p.m. can be expressed as 10y plus x, right? Because the numbers switched. And the number she saw at 14 p.m. or 2 p.m. can be expressed as 100x plus y, since there is an extra 0 between x and y. So now we're asking, what is the relationship between the distances traveled between 12 p.m. to 13 p.m. and 13 p.m. to 14 p.m.? And can you list the corresponding equation? Well, she's going at a constant speed, and the amount of time between these 3 sites are the same. So it means that the difference in the numbers should also be changing consistently at the same speed. Therefore, the difference from 10x plus y to 10y plus x is the same as 10y plus x to 100x plus y. So the distance traveled from 12 to 13, we have 10y plus x minus 10x plus y. And the distance traveled from 13 to 14, 100x plus y minus 10y plus x. So here's the solution. Let x represent the 10th digit of the number Karen sees at 12 p.m. and let y represent the 1st digit of the same number. According to the above analysis, the system of equations obtained is x plus y is equal to 7, because we know that the digit sum of x and y is 7. And we also know that this is equal to this. Solved, x is equal to 1, y is equal to 6. So the final answer is the number on the sign Karen saw at 12 p.m. was 16. Example 1. The sum of the 2 digit numbers is 68. Form 2 more 4-digit numbers, one with a greater 2-digit number to the right and the smaller 2-digit number to the left, and another 4-digit number with the greater 2-digit number to the left and the smaller 2-digit number to the right. The first 4-digit number is 2,178 more than the second 4-digit number. Find these 2-digit numbers. Wow, so that was a lot. Let's go one by one. So we know, let's set the larger 2-digit number as x and the smaller 2-digit number as y. So now we're not doing digits anymore, we're doing the numbers, because we're not given, because even if we did have digits, that would sort of just make the calculations more complicated, having more variables. If we just set it as x and y, however, it'll be simpler, there'll be less variables, and also this question doesn't really talk about the specific digits, but each of the two-digit numbers. So that's why we don't really have to set each of the individual digits as its own variable. So since the sum of the two-digit numbers is 68, we know x plus y is equal to 68. We also can express the first four-digit number as 100x plus y, and the second four-digit number as 100y plus x, and we know their difference is 2,178. Solved, x is equal to 45 and y is equal to 23. The answer. These two-digit numbers are 45 and 23. Practice. In a two-digit number, the digit sum is 11. If the tens digit and the ones digit are swapped, the resultant two-digit number would be 9 greater than the original two-digit number. Find the original two-digit number. Now I want you to pause the video, and from the experiences and the steps you gained from the previous problems, pause the video yourself and try to solve this word problem. All done? Okay. Here's the analysis. The key to solving the problem with a system of equations is to find the two equivalent relationships, right? This applies to every other type of word problem we have encountered before. Since both the tens and ones digit are unknown, the required two-digit number cannot be directly set. The two equivalent relationships in this question are tens digit plus ones digit is equal to 11, tens digit times 10 plus ones digit plus 9 is equal to the ones digit times 10 plus the tens digit. According to these two relationships, a system of equations can be set. Alright, so let's set x as the ones digit and y as the tens digit. Solved, x is equal to 6, y is equal to 5. Therefore, right, and this isn't even the final answer, we still have to put them back as 10y plus x, and that's equal to 56. So the final answer would be 56. When finding a multi-digit number, it is generally impossible to directly set the two-digit or three-digit number. So you can't just say that a three-digit number is A, or that two-digit number is I don't know, O. But you should set each of these digits as an unknown. The key to solving the problem is to identify the appropriate equivalent relationships, list the equations, and then solve. So the simple steps that every single other type of word problem involving systems of equations requires. Okay, now we're going to solve itinerary problems with systems of equations. Kaylee's route from home to school is a flat road followed by a downhill path. Assuming she walks at a constant speed of 60 meters per minute on a flat road and 80 meters per minute on a downhill road, then in 40 meters per minute on an uphill road, it takes 10 minutes for her to go from home to school, and from school to home, it takes 15 minutes to walk home. How far is Kaylee's house from the school? So if you've ever encountered ships on water problems where it's a ship and it's first sailing upstream and then downstream, this is sort of the same idea, whereas she's going downhill, she's faster than when she's going uphill. Analysis. The road from, okay, so this should not be Karen's house. This should be Kaylee's house. So, Kaylee's house to the school can be divided into two sections. One is flat and the other is sloped. So we know that this is the flat part, and she takes 60 meters per minute to walk this part. The sloped part, when she's going from up to down, this is a pointed down arrow. Downhill, it takes her 80 meters per minute. Uphill, it takes her 40 meters per minute. So the time spent on the flat road plus the time spent on the downhill road, right, that would be her time from going from home to school, and that would be 10 minutes. Time spent on the uphill road plus time spent on the flat road, which is going from school to home, back home, it's equal to 15 minutes. And remember, distance is the average speed times time. This is the very important formula to solve all itinerary problems. So let the length of the flat road be x meters and the slope of the hill be y meters long. So to fill in this chart, we know that the flat time would be x divided by 60. From school, that would also be x divided by 60. Y divided by 80, y divided by 40. And the total time is given in the problem, 10 and 15. So this is the following system of equations that can be obtained. Solved, x is equal to 300 and y is equal to 400. So therefore, the distance from Kaylee's house to her school is 700 meters. We can also solve this with method 2. Okay, so this should be Kaylee. Solution. The time Kaylee took going downhill took x minutes, and the time she took going uphill took y minutes. But can you spot the difference here? Instead of setting the distances or the speeds as variables, this is setting the times as variables. You can also solve it here. So we know the distance of the sloped road is 80x. This is 60 times 10 minus x. So we can set the following equations. 60 times the difference of 10 and x is equal to 60 times the difference of 15 and y. 80x is equal to 40y. Solve x is equal to 5, y is equal to 10. So the flat road distance is 300 meters, and the slope distance is 400 meters. Okay, so this should also be Kaylee. Oh my god. So this is Kaylee's home to school would be 700 meters. So right, to solve this problem, there are two different methods. You can either set their speeds, or you can set their times. So those solutions both work. Example 2. Karen and Kaylee each start at points A and B, 4 kilometers apart, and start at the same time at constant speed. If they're traveling in the same direction, so just to give you a sense right here, when solving itinerary problems, they're not always solved with systems of equations, so I'm sure you can visualize this. But it's always a good skill to just be mindful to make a sketch to remind yourself. So in lots of math competitions like Math Olympiad or Math Calc, they're going to give you itinerary problems. So this would be point A, point B. Karen starts here. Kaylee starts here. And I'm not really, this is not going to go in the National Museum of Arts, just something that can help you visualize. So you start at the same time, and this is 4 kilometers apart. And it gives you two different scenarios. If they're traveling in the same direction, Karen will catch up to Kaylee in 2 hours. So it says Karen catches up to Kaylee. Therefore, we're going in this direction. So they both go in this direction. So Karen catches up to Kaylee. So we know two things. We're first drawing it like this because Karen's catching up to Kaylee, and Kaylee has a head start of 4 kilometers. And we also know that Karen is faster than Kaylee because Karen was able to catch up to Kaylee. So this is 2 hours, 2 hours. If they're traveling in opposite directions, which is another scenario, they're going this way, they will meet in 0.5 hours. So they're now going towards each other and they're going to meet and say hello. So find the speeds of both Karen and Kaylee. Analysis. With itinerary problems, generally the quantitative relationships in the problem can be represented by a diagram, and then the equivalent relationships can be obtained. So a diagram, sketch, whatever. That's what I just did. And it's always a very good habit to help yourself visualize. So this is scenario number 1. If they're starting at the same time towards the same direction, right? So Karen travels for 2 hours. And this is the point where Karen catches up to Kaylee. This part, Kaylee travels for 2 hours. So the distance Karen traveled in 2 hours is equal to 4 kilometers plus the distance Kaylee traveled in 2 hours. Right, so this is, you can see here, this is the amount of distance that Karen traveled in 2 hours. This is also equal to the amount that Kaylee traveled at the same time plus 4 kilometers, which was her head start. What if they're starting towards each other? Okay, well, they go towards each other, they meet, and they each travel for 0.5 hours or 30 minutes. So the distance Karen traveled in 0.5 hours plus the distance Kaylee traveled at the same time is equal to 4 kilometers. So now out of those two equivalent relationships, we can set the equations. Let the speeds of Karen and Kaylee be x kilometers per hour and what? Okay, I'll set this as y. So and y kilometers per hour respectively. From the information given in the problem, we can set the following equations. So we know 2x plus minus 2y is equal to 4. 0.5x plus 0.5y is equal to 4. Solved, x is equal to 5 and y is equal to 3. So Karen goes at a speed of 5 kilometers per hour, and Kaylee goes at a speed of 3 kilometers per hour. Conclusion. So we start with the word problem, right? We set variables, identify equivalences, and one way to do that in this case is, we set charts, but we also drew. So we made a visual diagram to help us really understand what we're looking at here. Itinerary problems can sometimes get very, very complicated, so that's always a good idea. Set the equations, solve them, we have the solutions, double check, and we answer the word problem. So yeah, this is the cycle to solve itinerary problems with systems of equations. The two skills we learned today is to solve itinerary problems using systems of linear equations in two variables, and to also experience a different way of finding the equivalent relationships and just experiencing the process of solving practical problems with systems of equations. Remember, so we enforced the skill of setting charts, but we also learned how to draw basic diagrams for itinerary problems. Thank you so much for watching through Inquisitive Kids. If you liked our content, be sure to press the like button, press the subscribe button for more videos coming up, and see you next time.